Okay, section 2.5, the final section of Unit 2. We have already been through the first section where we verified a whole bunch of sort of random identities. And then we went on a spree of sections 2.2, 2.3, and 2.4 where we learned how to apply all those interesting formulas on our formula sheet, from sum and difference formulas, double angle formulas, half angle formulas, so on and so forth. So I guess what I'm saying in a way is that 2.2, 2.3, and 2.4 kind of all formed a neat little package together, with 2.1 being a little bit of a separate sort of thing, and now 2.5 is also going to sort of stand on its own a little bit. So we are kind of changing gears in the fact that we are now going to be solving trigonometric equations. So something you've done in math a lot, basically solve for x. Like, hey, take this equation and solve it for x. All right? So definitely kind of changing gears, right? Now, back in the old days, right, the old-fashioned way to solve for x when you first learned about solving for x was just about getting x by itself. You know, add stuff to both sides or divide both sides by something just in order to get the x alone. But not what we can do here, you know, if we're trying to figure out like the sine of x equals root 3 over 2, and we want to know what x equals. So we're going to have to do other kinds of stuff. Now, this is actually a pretty basic example to start off with. The sine of what equals root 3 over 2. Now, let me show you a bunch of stuff. Okay. Now, the sine of an angle, as far as triangles go, SOHCAHTOA, is equal to the opposite leg over the hypotenuse. And since the sine of x can be positive when angle x lies in quadrant 1 or quadrant 2, one way to go about this is to draw a picture and draw triangles in quadrant 1 and quadrant 2, kind of like we did back in Unit 1, right? So since the sine can be positive root 3 over 2, in these two quadrants, you draw these triangles in those quadrants. And having known the answer, like having the final answer of root 3 over 2, we can label the sides based on the fact that sine is equal to opposite over hypotenuse. And so the opposite leg, in a way, is root 3, and the hypotenuse is 2. Opposite of the reference angle. And from there, you know, from the answer, we can kind of figure out what the reference angle is. So what do you think the reference angle would be if the hypotenuse is 2 and the opposite leg is root 3? What kind of triangle would this be? And what would this angle be? Well, wouldn't this be a 30, 60, 90 triangle? With the angle here that's across from the root 3 is 60. So, I guess that leads to knowing that this angle is just 60 and this quadrant 2 angle, right? And remember, people, you know, this quadrant 1 angle, that's just 60, but this quadrant 2 angle from here to there, if 60 is the reference angle, that would be what? That'd be 120 degrees. All right? Now, let me say at this point in time that it might have occurred to you, just looking at this original equation, the sine of something equals root 3 over 2, it might have occurred to you just to think, well, can I just go on my calculator and do the inverse sine of root 3 over 2? And you're not, totally wrong, especially with these fancy yellow calculators I have here in 2018. If you're in the right mode, like math print mode, it's probably going to give you a really nice answer. Actually, what am I saying? You probably don't even need to be in a certain mode. I guess you just got to be in degree mode. But here's the thing. That's cheating. That's kind of cheating in a way. But more importantly, way more importantly, I don't think the calculator will give you both of these answers. The calculator is only going to give you one of those answers, probably the 60 degrees. But that's just assuming that there's only two answers. Look down here. How many solutions are there? How many solutions are there? Are there just two? Like, yes, if you did the sine of 60 degrees, you'd get root 3 over 2, right? And if you did the sine of 120 degrees, that would also get you root 3 over 2. Is there no other angles that the sine of it would be root 3 over 2? Think about it. I mean, are there no like negative angles that you could take the sine of and get root 3 over 2? Are there no angles greater than 360 degrees? What if you had an angle that was basically coterminal with 60? Essentially the same as 60 degrees, just coterminal. Wouldn't the sine of such an angle be also root 3 over 2? Like, how about 420 degrees? Isn't 420 degrees coterminal with 60? Yeah. So, how many solutions? Technically, there is an infinite number, because there is an infinite number of coterminal angles for 60, and there's an infinite number of angles coterminal with 120. So technically, there's an infinite number. So yes, like just doing the inverse sine on your calculator, I'm not really going to emphasize that here, especially when technically there's an infinite number. Now, so we have this method, and I want to point your attention, getting a little ahead of myself in a way, but look a little bit to the next example in our notes, the next section of the notes, where it says to solve, and then it gives you this interval for x. So that's basically saying solve for x, but we only want answers for x that are between 0 and 2 pi. Translation, between 0 and 360 degrees. Okay, because here, without that stipulation, what you actually have to say technically is that my x would be equal to 60 degrees plus 360 degrees times n, where n could be whatever integer, like it could be any integer, you know? So this represents right here all the infinite answers that are coterminal with 60, you know, thinking that n could be whatever integer you want it to be. And you would also have, in a manner of speaking, another infinite number of answers, 120 degrees plus 360 degrees times n, you know, because you could also have all those coterminal angles for 120. And if you're thinking, well, what about minus 360? That's included because you could have, like I said, n could be any integer, even negative integers, of course. So this is how you would have to technically write all infinite number of answers if you weren't given like an interval where, like, okay, we only want the answers that are between 0 and 360. Okay? So, now before we start doing example after example after example, you may be allowed to just use your cheat chart instead of drawing like this picture. Okay? If you just get your equation down to the sine of whatever equals whatever, or the cosine of x, whatever x equals whatever, you know, you might just be able to go on your chart and see, you know, what angles, you know, that works with, but we'll see. But here, looking at this first example, 5 times the sine of x equals 3 times the sine of x minus root 3. The first thing we're going to have to do is get the sine of x's together and basically get the sine of x by itself, kind of like this was. You know, once you get the sine of x by itself, or the sine of whatever by itself, or the cosine of whatever by itself, or the tangent of whatever by itself, that's when you can pretty much draw a picture or just go to your cheat chart. So the first thing we're going to have to do here is subtract the 3 sine of x over to the other side and get to here. So we have 2 sine of x equals negative root 3. And there's one more thing we have to do to get the sine of x by itself, which is what? Divide both sides by 2. So we divide both sides by 2 and we get the sine of x all by itself. Now we can look at this and actually start to think about what x could be. Does it make sense? Once you get this sine of whatever by itself, you can start to really get to the point where, which is like, okay, what could x be if the sine of x is equal to negative root 3 over 2? Now, you could go through the whole picture stuff where the sine of whatever could be negative in these two quadrants, which means you draw pictures in these two quadrants and you use SOHCAHTOA to label the triangles. So it would be negative root 3 opposite over 2 is the hypotenuse. And that means these reference angles are 60 degrees. And so the quadrant 3 angle would be, the quadrant 3 angle would be 240, and the quadrant 4 angle would be 300, which you might just be able to go to your cheat chart. You know, once you get to here, you might just be able to go to your cheat chart and say, okay, the sine of what gets you this answer? Well, those two angles. Remember, there's two angles between 0 and 360 or between 0 and 2 pi. And so those are my only two final answers because of this interval. Example 2. The tangent of 2x equals root 3. Well, guess what? Even though this says 2x, we can just cut right to the chase when it's like, okay, the tangent of what equals root 3. So in other words, we're going to figure out what that 2x is, or what that 2x could be. So we can already consider the tangent of whatever all by itself, and we can go right to our cheat chart or go right to these pictures, okay? Because, again, we're going to figure out what 2x could be, which will lead to us figuring out what x could be. And so it figures out that 2x could equal what? Well, if so the tangent of what is root 3? It looks like 60 degrees in quadrant 1, or what's my quadrant 3 solution? 240. So 2x could equal 60, or 2x could equal 40. But remember, people, we want x. So x could equal 30 degrees, or x could equal 120 degrees. When you just take these two simple looking equations and solve for x, get x by itself. Divide by both sides by 2. Now, plot twist. Hopefully that's sunken in so far. This whole 2x ordeal where, again, just figure out what 2x could be and then just solve for x. So I hope that's sunken in. If not, pause the video, think about it, I don't know, replay some things. But because, plot twist here, because of coterminal angles, and because we are dividing by 2 to get x, we also have to consider the fact that 2x could equal 420 degrees. Where did I get 420 degrees? By double dipping on 60 degrees. If I thought about what is coterminal with 60 degrees, I get 420. So, because again, 420 degrees in a way is the same as 60. They are coterminal. So again, like I said, I'm like double dipping on the whole 60 degree thing. And now look, I know 420 degrees is too large for our interval. But the thing is, it's not what 2x equals, it's what x equals. And we're dividing both sides by 2 and getting that x could be 210. So guess what, people? 210 is in our interval. So guess what? 210 is a third answer for us. And we're also going to double dip on the 240. So what angle is coterminal with 240? All you got to do is add 360 to it. So double dipping on the 240, 2x could also equal 600. Now I know, again, 600 is too big, but when we divide both, because we just care about x, not 2x, and we get x equals 300, which is a legitimate, good, fourth answer. It's another legitimate answer. So we have 4 answers, okay? Now, should we triple dip? What if we went around the circle again for what, like 780? So yeah, 2x could also equal 780 if you add 360 again. But, even when you divide by 2 from 780, like it's going to be, even x is going to be too big for our like acceptable interval. So we're only double dipping on the 60 and the 240. And so 4 final answers. Number 3. So cosine can be positive in quadrants 1 or 4. And now look, drawing the picture might end up being not something you even need to do, right? So it's likely to be true that we could, at this point in time, just go to our cheat chart and realize that, the cosine of what equals root 2 over 2. Except, it'll be what x over 3 equals and not yet what x equals. So going to your cheat chart, this x over 3 could equal 45 degrees or 315 degrees, which makes sense considering, 45 degrees is in quadrant 1 and 315 degrees is in quadrant 4. But so this is what your cheat chart could say. But again, like, this angle would be x over 3, and we ultimately care about x. So solving each of these for x would mean we have to what? Multiply both sides by 3 to get 135 or 945. Well, I hope your immediate reaction to 945 is that it's just too large for our acceptable interval. So 135 is good, it's in our acceptable interval, but 945 is not. Now, should we check coterminal angles? Like, should we double dip on the 45? If we added 360 to 45, like if we went all the way around the circle again, that would be 405 degrees. So you could say, theoretically, that x over 3 could also equal 405 degrees, because that's like the same as 45. But we're going to be we're not going to be like dividing the 405 by 3. We're going to be multiplying it by 3. I mean, 405 is already too big for our acceptable interval for our answers. And so multiplying by 3? No. So we are not going to check coterminal angles. Okay, so really, we only have one final answer. That's it, just one answer. All right, so hopefully that all made sense. From example 1, just quick review. We always want to get the sine of whatever by itself, or the cosine of whatever by itself first, if we have to. In number 1, we had to do a couple steps to get the sine of x by itself. In number 2, we didn't have to do a darn thing to get the tangent of 2x by itself. It was already by itself. And in number 3, the cosine of x over 3 was already, the cosine of whatever was already by itself. And once that part is by itself, you can go to your pictures, or you could just go to your cheat chart. Okay? And once you figure out what two angles are on your cheat chart or in your picture, you can start to think about whether or not you need to kind of start double dipping or triple dipping on the angle. Like here, it was just the sine of x, you know. So you could say, like, you know, you could like double dip on this one and get 600 degrees, but that it would just be x, you know. Like x, this is just x here, x could equal 240, or x could equal 600. So there was no double dipping here. But here it was what 2x equaled. And since we were dividing by 2, like since we were taking our two angles and dividing them by 2 to get down to like x, we were going to double dip because we were dividing. We were taking a number that was too large for our final interval, but we were dividing by 2. And so x actually ended up being like in our interval. All right, so yes, when in this kind of situation you're going to double dip, or if it was like 3x, you'd actually triple dip. And then in this situation, it also turned out that we were not going to double dip. You know, we didn't even have 2 good answers, let alone 4, because we only ended up with 1 good answer for x. All right, now let's move on to number 4. We're starting to get into like a little bit new level of difficulty. So look at number 4, 2 sine squared of x minus 3 sine of x plus 1 equals 0. Does this look like anything to you? Does it remind you of anything? You know, I mean, remember, the idea is maybe to get the sine of whatever, in this case the sine of x, by itself. Can we even do that? Can we even get the sine of x by itself? No. So if you haven't sort of thought of this already, you want to treat this like you would treat back in like your Algebra 2 days. 2x squared minus 3x plus 1 equals 0. How would you have treated that? How would you have solved this for x back in the day? Wouldn't you have tried to factor? Yeah, and so we're going to basically factor this by the Phoenix method. So just like you might bust out a method like the Phoenix method to factor 2x squared minus 3x plus 1. So our Phoenix here, okay, the number that's complicating things in the first place, is the 2. Because if that 2 wasn't there, the unfoiling, the factoring, would be a whole lot simpler. So that 2 is the Phoenix, and as we go through the steps of the Phoenix method for factoring, we multiply the 2 to the other end, right? We multiply the 2 to the 1. And now we can unfoil, you know, a bit easier. So what 2 numbers multiply to get positive 2, but they also add up to negative 3? Well, negative 2 and negative 1, of course. And then at this part, this spot in the Phoenix method, we bring the Phoenix back to life. We divide the 2 in there, and then we reduce any fractions we can, because we've just created 2 fractions, and so we now want to reduce the fractions if we can. This one will just become 1 over 1, or 1. This one will not reduce, and so we bump up any leftover denominators, and so this just becomes 1. This 2 bumps up, and we get final bubbles of this. Okay? So again, what have we done at this point? We've recognized that we can treat this the same way we used to treat stuff like this, except instead of just having an x here, we have a sine of x. Okay? So like the bubbles for this would have been just x minus 1 and 2x minus 1. But here, we don't just have x, we have sine of x. So here is our final bubbles. And as always, after you factor, and the other side equals 0, of course, you set both factors equal to 0, and you work with each one independently. You solve each one independently. Remember, the whole idea was try to get the sine of x by itself. Now we can. The sine of x equals 1. You add 1 to both sides. And when you add 1 to both sides and then divide both sides by 2, you get the sine of x equals 1/2. Okay? And let's just kind of cut to the chase. No pictures needed here. Well, let's show the pictures. For this guy, it'd be like we would draw a circle. For this one, we draw triangles. But, let's say you're just going to your cheat chart here. And if the sine of what equals 1, 90 degrees. So from this equation, okay, we get an answer of 90 degrees, and just that's it, just one answer. Only the sine of 90 degrees equals 1, unless you're going to start double dipping and going with coterminal stuff. So x equals 90. Now, would we double dip? No, because it's just x. So if we double dip, it's going to be too big for x. And then from this guy, it ends up being a couple answers on our cheat chart. 30 degrees or 150 degrees. And so we have 3 final answers to this problem. This one looks like it's going to be very similar, but in a way. But first, I think we need to get that cosine squared, if we can. If we can. And we can. Right? So we can get the cosine of whatever by itself. But first, we've got to get cosine squared of x by itself. So we'll add 3 to both sides, then divide both sides by 4. And what's the final move here? To get cosine squared of x into becoming just the cosine of x. Well, I think we're going to take the square root of both sides. But, as this should make sense to you, whenever you take the square root of both sides, solving for x, or in this case, solving for the cosine of x, we get plus or minus whatever. Okay? Now notice how I actually was able to take the square root of 4, and that's where the 2 comes from. Can't really do the square root of 3, so that just stays the square root of 3, but the square root of 4 is 2. So plus or minus root 3 over 2. And now, hey, just like that, I think we're ready just to go to our cheat chart. The pictures would be like so, because cosine would be positive something in quadrants 1 and 4, but negative in quadrants 2 and 3. But just going to your cheat charts, from this one, you would get 30 degrees or 330 degrees, and from here, you'd get 150 degrees or 210 degrees, because the reference angle in your pictures would be 30. Okay, so example like this, we were able to actually get the cosine of x by itself. We had to end up doing a square root of both sides, and that ended up with like a plus or minus deal, but we were able to do it. Number 6. Getting a little interesting here. So what are we going to do number 6? Not only do we have a sine of x, we have a tangent of x. So it's like, again, like what's the priority? Getting the sine of x by itself, or the tangent of x by itself. I don't think we're going to be able to do that. So what did we kind of do back here? You know, like if you can't get something by itself, maybe we can factor, or but what do you always have to do before you factor? Don't you have to set it equal to 0? So let's try that. Like this is a weird looking example, especially to you first time rookies out there. This is a pretty scary, maybe even a very intimidating example problem, but I mean, look, here's where we're at. I don't think you're just going to be able to get the sine of x by itself or the tangent of x by itself. So let's see what happens when we set it equal to 0 and see about factoring. Let's see. So we have to subtract sine of x to the other side. Set equal to 0, our go-to move here. And can this factor? You bet it can, because what's the first method of factoring we always have to check? GCF, of course. And since both of these terms have a common factor of sine of x, we can factor that out as a GCF. And what do you always do after you set equal to 0? After you factor, you set the factors equal to 0 separately, and you go from there. Hey, check this out. So the sine of x equals 0, that's already good to go. We could check the cheat chart on this. Sine of x is by itself. And then over here, I think we could get the tangent of x by itself real easy by just adding 1 to the other side. So we get to here. So we have sine of x equals 0. We can go to our cheat chart for that. When does the sine of x equal 0 according to your cheat chart? Well, when x equals 0 degrees or when x equals 180 degrees. And when does the tangent of x equal 1 according to your cheat chart? Well, when x equals 45 degrees or x equals 225 degrees. And no double dipping here, because it's just x, and it'd be too big on all these. So we have 4 final answers. And in case you're curious, this would be the picture you would draw for the sine of something of x equaling 0. And this is the picture you would draw for the tangent equaling 1. And it looks like that reference angle would be 45 degrees, of course. And those are all the different kinds of examples that I guess I needed to show you for section 2.5.